Hello, welcome to the JINA-CEE live stream event. Today we're going to be discussing the impact of the LIGO Virgo neutron star merger discovery on research in nuclear science. I'm Luke Roberts at Michigan State University, and I'm going to be moderating today. So our aim is to foster discussion about new research directions in nuclear physics and astrophysics that have been opened up by the multi-messenger signals from this merger and hopefully more mergers to come that we detect in gravitational waves. So we're going to have a number of short talks about the observations themselves and the interpretations of these observations, as well as what the capabilities, experimental nuclear physics capabilities are for measuring some of the properties about nuclei we might want to know for these events. And then we're going to have a panel discussion about next steps and questions about this event, including the speakers, as well as some other panelists. The panel will address questions from the audience. So if you have questions either during the talks or during the panel discussion, you can either tweet them to us using hashtag GWNuclear, so you can see that behind me, or you can find that online. Or if you don't use Twitter, feel free to send them by email to gwnuclear@nscl.msu.edu. And so rather than answering questions after each talk, we'll sort of aggregate all the questions and save them for the panel discussion. So if you have questions during talks, please just tweet them to us. So today we're going to have 5 speakers. We're going to hear from Duncan Brown at Syracuse University, who's a gravitational wave astronomer. We're going to hear from Mansi Kasliwal at the California Institute of Technology, who's a time domain astronomer, to tell us about the electromagnetic signals that were observed in coincidence with GW 170817. Dan Kaysen is also going to tell us about interpreting these electromagnetic signals. So he's a theorist at UC Berkeley. Jocelyn Reed at Cal State Fullerton is going to talk to us about interpreting what the gravitational wave signals mean for neutron star radii and neutron star properties. And then we're going to hear from Artemis Spru at Michigan State University, who's a nuclear experimentalist, and she's going to tell us about current and next generation nuclear facilities that can help us make measurements that can inform these observations. We're also going to have panelists, Ani Abrahamian, who's at Notre Dame, who's a nuclear experimentalist, Andreas Bauswein, who's at the Heidelberg Institute for Theoretical Studies, and who's a theorist who works on modeling neutron star mergers. We're going to have Jim Latimer, a theorist at Stony Brook University, and we'll also have Brian Metzger, a theorist at Columbia University, on the panel. So our first talk today will be from Duncan Brown about just what the gravitational wave detections from GW 170817 are. So thanks, Duncan, for joining us. And if you have any questions while Duncan's talk is going on, feel free to tweet them and we'll collect those for the end. So go ahead, Duncan, welcome.
Okay, thank you, Luke. Let me share my screen so you should be able to see my talk. Okay, can you see that?
Yep.
Great. Okay, so thanks for inviting me. I'm going to give an introduction to GW 170817, the neutron star merger that was observed in gravitational waves and across the electromagnetic spectrum. I'm just going to talk about the gravitational wave detection and also briefly mention the gamma ray burst detection as they happened within a couple of seconds of each other, and then I'll leave it to Mansi to talk about everything else electromagnetic. So let me start with this slide, which is a diagram of advanced LIGO, the Laser Interferometer Gravitational Wave Observatory. This is a dual recycled Fabre Pro detector. It's the second generation ground-based gravitational wave detector. I won't go into too much detail on the way the detector works. All I'm going to say is that this is the schematic design of the detector. If you build a detector that performs exactly to the design that we are hoping to see, that the noise curve on the right, so the graph on the right shows gravitational wave frequency on the x-axis, and the amplitude spectral density of the noise in the detector on the y-axis. And this is the predicted total noise in the detector. Advanced LIGO is basically a quantum noise limited detector across much of the band, with a little bit taken out from the mirror coating noise in the middle. This is the expected sensitivity of advanced LIGO once we reach design. Let me say that, at this sensitivity, we're seeing binary neutron stars to an average distance of over 200 megaparsecs. The universe seems to really like gravitational wave astronomers because LIGO is not yet at this sensitivity, and we've already seen too many binary black holes for me to remember the exact number off the top of my head as what's public and what's not, and one binary neutron star detection. And the two things to say is that our first binary black hole detection was unambiguously loud, and our first binary neutron star detection, which is shown on this slide, was also absolutely screaming loud. It was actually louder in network SNR in the detectors for the binary neutron star detection than the GW 150914 binary black hole detection was. So this is the loudest gravitational wave signal that we've seen to date. This slide shows the gravitational wave signal seen in the three detectors. So the x-axis on this slide is time in seconds, and unlike our binary black holes that show a fraction of a second of merger signature, you can see starting 28 seconds before the end time of the signal, stretching all the way. And I claim if you squint, you can look closely in Livingston, you can see a trace of the signal in the data. This shows a time frequency spectrogram of each of the detector data outputs. So the y-axis here is gravitational wave frequency, and the color shows the normalized amplitude of the time frequency decomposition of the detection. And you can see the binary neutron star signal sweep all the way through the band in Livingston. You can start to see it sweep from around 40 hertz or so by eye in Hanford up to a merger frequency where it starts to disappear in the noise around 500 hertz. Now remember, this is a visual representation. We actually do both the detection and parameter measurement using match filtering, using a match filter likelihood, and the match filter can see the signal in the detector data for order 100 seconds in the detector data. So this is it's so loud you can see it by eye in the detector data, but the filtering and the parameter measurement can see it for longer than even you can see by eye in these high frequency spectrograms. Livingston was our most sensitive detector. Hanford was less sensitive, and Virgo was the least sensitive of the three detectors. You can't actually see the signal in the Virgo detector. That's mainly because of the orientation of the source with respect to Virgo. LIGO Hanford and LIGO Livingston are almost aligned with each other up to the curvature of the Earth. Virgo is in Italy, and so is misaligned with the Hanford and Livingston detectors. If this signal had been well aligned for Virgo, it would have been visible in the Virgo detector data. But it was near a dead spot of the Virgo detector's antenna pattern. The gravitational wave detectors are not uniformly sensitive to the whole sky, and the fact that we didn't see a signal in Virgo, given how strong it was in the LIGO detectors, gave us very good sky localization. In fact, I think much better than many of us was expecting to get for a few years. On the next slide, this is the gamma ray burst signature and the gravitational wave signature. So the probability of a chance temporal and spatial coincidence of the gamma ray burst that was seen by the Fermi GVM detectors, an integral, is 5 times 10 to the minus 8. So we have just from temporal and spatial coincidence of GW 170817 and GRB 170817A, we have a 5 sigma association of the gravitational wave merger and the gamma ray burst that was seen by Fermi and integral. And so we can pretty much conclusively say that this gamma ray burst, short hard gamma ray burst, and binary neutron star merger are associated with each other. And the time delay between the end of the gravitational wave signal and the start of the gamma ray burst is 1.74 seconds, which is an important number that Dan and others will talk about later. So we have very quickly an unambiguous association between a gamma ray burst signature and a gravitational wave signature. So let me just explain a little bit how this was discovered. So this is the discovery screen that we see. And we realized we had a significant signal on our hands. We have a suite of automated software called GST-LAL that runs online, looking for binary neutron star and binary black hole mergers. And at 8:47 a.m. EDT, it submitted an event. That event was flagged just in the Hanford detector, but had a very high significance. So a false alarm rate, that means the chance of this coming from noise was less than 1 in 9,000 years for this. Well, we looked at it, and it has a high signal-to-noise ratio. So just in the Hanford detector, its signal-to-noise ratio, the match filter signal-to-noise ratio is 14, which is very large for a binary neutron star event. And you can see that we saw quickly the low chirp mass, 1.2, and total mass, 2.8, strongly suggests that this is not another loud binary black hole, but is in fact a binary neutron star candidate. So very quickly, we realized that this was a possible binary neutron star source. And we also had, we're plumbed into Fermi GBM alerts, and we saw that there was a Fermi gamma ray burst event 2 seconds after the merger. So this got us extremely excited that we were seeing something, a loud possible binary neutron star event coincident with a trigger. But the trigger was only seen in Hanford, even though Livingston and Virgo were operating. So there was some level of scrambling to figure out what was going on. When we took a look at our detector data, we realized that there was actually a glitch in the Livingston detector data at the time of the signal that prevented us from the automated software from seeing it. But we went back in with another piece of software that does the reanalysis, that looks for binary neutron star signals. We rapidly reanalyzed the data, and this plot shows time on the x-axis in seconds, and match filter signal-to-noise ratio on the y-axis. And you can see those two beautiful clear peaks there with a nice strong Livingston signal and a nice strong Hanford signal. This was the reanalysis after we mitigated the glitch in the Livingston detector data. So after the humans went in, figured out what was going on with Livingston, there was a fraction of a second of data that was corrupted compared to this 100-second long binary neutron star merger. And we saw we had a coincident event in Hanford and Livingston. You'll notice that the Virgo signal noise, which is shown in green, doesn't peak within the time delay window that you would expect from a Hanford and Livingston signal, even though the signal is so strong it should have been seen in Virgo. The reason for that is, as I said before, it's near the dead spot of the Virgo detector, and that gave us extremely good sky localization. So we used this software called Baystar to do the sky localization. The brown region shows you the region we would have got sky localization from Hanford and Livingston alone, but with a constraint we get from Virgo of the absence of signal there, we narrowed it down to a much smaller region, and a small enough region for electromagnetic follow-up partners to go after that and get it very quickly. In fact, we're only limited by the location of telescopes and the rotation of the Earth. We didn't actually miss anything electromagnetically because of the delay of doing the data analysis and mitigating the glitch. So at 1:45 p.m. EDT, we sent out an alert with sky localization. We refined the event, sent the sky localization out, flagged it as a very significant trigger at a luminosity distance of about 40 megaparsecs, which is very close for a very loud signal, and then set the EM partners to go on that. And Nancy will talk about that in a second. Let me just briefly review the parameters of the signal. I'm just going to discuss the individual component masses here. Jocelyn will talk about the implications of the signal for the nuclear equation of state. This strongly looks like a 1.4 solar mass binary neutron star merger. The problem is with gravitational waves, as you may know, we don't measure the component masses very well. What we measure very precisely is the chirp mass, which is that combination M1, M2 to the 3/5, M1 plus M2 to the 1 over M1 plus M2 to the 1/5. That we get extremely accurately. And if you plug in equal mass ratio there, that comes out as basically 1.37 equal mass. But when you actually try and measure the masses without a prior on the mass ratio, the plot on the left shows what you get, either for a very coarse, eyes wide open, large spin. This number chi is the neutron star spin. But if you restrict down to more plausible neutron star spins, you get the beige region there. And so it looks like this is an equal mass binary neutron star, about 40 megaparsecs. I've given the range on M1 and M2 there. The broadening of the range on M1 and M2 is because of the lack of ability to measure the mass ratio compared to measuring the chirp mass. This slide shows the connection to the gamma ray bursts. One thing to note here, this is a figure from the LIGO Virgo Fermi integral gamma ray burst gravitational wave detection paper. What this shows is the redshift of GRBs, short GRBs and long GRBs with no redshifts, and the luminosity of these GRBs. The blue are the short GRBs with a known redshift, and the pink dotted line is approximately the sensitivity of the GBM detection sensitivity to GRBs as a function of redshift. Now, this GRB was pretty faint. It was just on the edge of being able to be discovered, given that this source is at 40 megaparsecs. So one thing to note is the gap between this green star here, which is GRB 170817A, and the rest of the population. And this has us all wondering if there's a faint population of GRBs out there, and the neutron star rate is people previously thought that GWs might be difficult to get, might be at large distances or at large redshifts, but it's looking like there's actually this nearby population that we may get a few more of these in the years to come. Speaking of what's going to happen in the years to come, this is the figure from the 01 binary neutron star upper limit paper that shows a range of predictions for the binary neutron star rate in per cubic gigaparsec per year, and the 01 upper limit of what we excluded from not detecting anything in 01, as well as the predictions for the possible 02 and 03 ranges for the 02 run and future runs. If we superimpose the measured rate, and measuring rate with one source is always tricky, so it has pretty large error bars, but the measured rate of binary neutron star detections from GW 170817, that gives us a rate of 1,540 per cubic gigaparsec per year, and is shown in that yellow region here. And this is nice because at the upper end of most of these rate predictions, it looks like we're going to be seeing a fair few of these things moving forwards. So let me lead into Mansi's talk with this movie that basically shows the localization region from Fermi of the GRB, the Fermi and integral region using the data from the integral GRB detector. The overlap of those regions is that blue area right there. In a second, this is going to show the LIGO localization, so this is LIGO only. And then when you add in the Virgo detector, you get this very nice error region here. You can zoom in on this, and then this is the point where the EM follow-up takes over. So I will let this movie play. I will stop here and hand it over to Mansi.
Thanks very much, Duncan, for that very nice talk. So if you have questions for Duncan, please put them up via Twitter using the hashtag GWNuclear, or sending email to us at gwnuclear@nscl.msu.edu. And so as Duncan said, next we're going to hear from Mansi Kessliwal at Caltech about the electromagnetic signals observed in conjunction with the gravitational waves from GW 170817. So welcome, Mansi, and take it away.
I'll pick up. Thus began the most exciting morning in the life of many astronomers, time domain astronomers in particular. So we started the hunt of which galaxy it really was amongst only 49 galaxies in this very, very well localized signal. And the way we did that is that we cross-matched the information from the gravitational waves on the localization, not only distance, but also volume with the galaxy catalogs. And then we prioritized our search based on parameters of the galaxy, in particular the stellar mass, because the expectation is that the more massive the galaxy, the more likely it is to be the home of the merger. So we began searching down this list, marching down this list with multiple telescopes at multiple wavelengths, since at least here at Caltech, we tend to be a little bit model agnostic when looking for the first of anything. So we began a panchromatic hunt at 4 different wavelengths and just marched down this galaxy list. And so this is a list of 49 galaxies, and we began a search in the hard X-rays, the soft X-rays, the UV, the infrared, and the radio. And then there were many, many more teams doing optical and infrared searches, in particular in Chile, because if you noted the array and deck in the localization, it was very nicely accessible from the southern hemisphere, but it was very close to the sun. And the first country where the sun set after the localization was announced was Chile. So there were 8 telescopes, again, adopting different search strategies, different galaxy catalogs, different filters, the details, but all began searching in that 2-hour window after sunset to find the electromagnetic counterpart. And within minutes of sunset, the Carnegie Observatory's group, with using a very tiny 40-inch telescope, announced a possible candidate counterpart. You see this bright dot here that wasn't there before. There's a convenient red arrow which didn't come, with the image when it came, and they were the first to announce the coordinates. And this was fantastic because within minutes of this announcement, and this is one of the most majestic aspects of this discovery, was that within minutes of this announcement, there were detections of this electromagnetic counterpart in the ultraviolet by the Swift satellite, in the infrared, in the optical, at least in these 3 wave bands, all within a day after merger. And what was spectacular was that even after much of a wait, which was about 9 days in the X-rays and 16 days in the radio, even the X-ray and radio emission was detected from this electromagnetic counterpart. So there was light at every wavelength. And that to me is just scientifically amazing because it gives you information to put together a complete astrophysical and astrochemical picture of what we were seeing here. And this was a global effort by many, many telescopes. Actually, I think it was a total of 70 telescopes worldwide, including 7 telescopes in space. And I think every continent, there's even a telescope in Antarctica that was observing. And this little movie here that you can see time ticking on the top right. And as the sun sets in the different countries, you see the optical and infrared telescopes observing. The green dots are radio, and you'll see that the radio lights up even in the daytime because the radio is immune to the sun. But this was a spectacular effort with, I think, 2,000 or 3,000 astronomers involved. And on the day of the announcement, there were 84 papers on archive describing the electromagnetic counterpart and how it relates to the gravitational wave, the discovery of the first binary neutron star merger. Of course, one other advantage of having a globally distributed team, which I'm lucky to have here, is that the team never sleeps. The sun never sets, and the telescope can keep observing. But the team also is continuously working. And there's a lot of excitement in this team. Here you just see pictures of the real powerhouse of such teams, which is the young students and postdocs, looking at the data as soon as it comes in, each one taking ownership of one of our 18 telescopes that were involved here and reducing the data as soon as it comes and triggering the next observation. Because this transient was full of surprises. This was the first time we were seeing something like this unfold. So everything had to be done dynamically in real time in terms of triggering telescopes, planning and optimizing search strategies. And the young people, the students and postdocs, really played a key role here. So this here now is a compilation of the ultraviolet, optical, and infrared light curve. So you can see that the ultraviolet light fades very, very quickly. It's gone in just a few days. This is data from the Swift satellite and these late points here from the Hubble Space Telescope. You can see the optical lasts for a few more days, maybe about 8 weeks or so. And the infrared, the JHK bands, these are the near infrared bands, they evolve relatively slowly for a good 3 weeks or so. And you can now combine this to form a bolometric light curve. But one thing is already clear at this point, is that this transient was very bright and very blue at early times. And while this is puzzling from explaining it from a model point of view, this makes observers really happy because bright and blue means it's easy to find, and so that's good news. Of course, astronomically, one of the most spectacular aspects of this discovery was the nucleosynthesis and understanding our process nucleosynthesis. So as of August 16th, we knew that hydrogen and helium come from the Big Bang. The elements shown in blue here come from different flavors of supernovae. But until August 17th, we had no idea. Or, to be fair, there were a lot of predictions by people such as Latimer decades ago, theoretical predictions that the place where our process nucleosynthesis and the place where all these heavy elements shown in yellow here are synthesized should be merging neutron stars. But for observers, seeing is believing. And this event was our first opportunity to see two neutron stars merge. And it was actually quite amazing that we could also see evidence of our process nucleosynthesis and the formation of these heavy elements. So here I show you the first spectrum that my group took at Gemini Observatory. And when my students would use the spectrum, I couldn't believe it. There were these two broad bumps that you see here in the spectrum. That's the data in gray and black, smoothed. And in red, you see model predictions from Dan Kaysen and Jennifer Barnes from 4 years ago. This is not fitting the data. This is just overplotting Dan and Jennifer's work. And these are predictions for what our process nucleosynthesis elements and the radioactive decay, if you take into account all the opacities correctly, look like. And it was really very, very surprisingly close. So I hope Dan will tell you more about this. And there's a beautiful spectroscopic sequence. Here I'm showing you a sequence taken by my collaborator, Elena Pian, with the very large telescope of the ESO Observatory, the European Observatory. And you can see as time ticks, you see the spectrum evolve from something very hot and blue to something which starts to show bumps and wiggles, which are probably blends of many different elements. The guesses are starting to trickle in the literature, and Dan can tell you which ones to believe and which ones need a lot more work in the next talk. But you can see that there's a lot of information at almost 1 day cadence, all the way from the UV, optical, and infrared of how the spectra evolved as a function of time. And the data collection continues because even after this target became very close to the sun, we continue to detect it with the Spitzer Space Telescope. And this now is probing the reddest emission and also in the nebular phase, so has additional clues on the nucleosynthesis. And what I hope some of this audience will be experts in is, again, the distribution, the relative abundance of these elements. Do we really need all three peaks to explain this? Is the amount of material that's made here multiplied by the rate equal to the solar abundance? There's a paper by Stefan Rosberg which says that we just need the first peak and the second peak. Maybe a little bit of lanthanides would help, but we don't need the third peak at all to explain the data in hand. So I think all of these are open questions, and I think there are many, this is the beginning of trying to understand all these puzzles. But I wanted to take the last couple of minutes just to give you a sense of an astrophysical picture of how we can put together all the different data, the different wavelengths to explain what we are seeing. And there's somewhat of a misconception that what we are seeing is a gamma ray burst. It was not on axis. I think everybody agrees that it was not on axis. But as Duncan showed you, it was a very, very weak burst of gamma rays. So it's almost a misnomer to call it a gamma ray burst because it was 10,000 times weaker than a typical short-haired gamma ray burst. And the radio and X-ray was really a very, very long and patient wait, a surprisingly long and patient wait. And it has a very surprising signature, which is at odds with the gamma ray signature. So whether you talk about an on-axis or a slightly off-axis GRB, you need it to be slightly off-axis to explain the gamma rays, but the radio and X-ray require it to be widely off-axis. So the canonical picture of an ultra-relativistic jet just doesn't work. So one idea, one of many ideas I hope that people will be thinking of to explain what we are seeing here is the idea that we proposed called the Cocoon Breakout. And the idea here is that on the left, you see the energetics, so you see energy density. On the right, you see the log4 velocity, so you see the velocity and kinematics. So as the jet launches, basically the point is that the jet is not launching in a clean environment. The jet is launching in an environment where there has already been several tenths of solar mass of material thrown out into the surrounding medium, even before the merger. So the jet simply gets stuck. And the stuck jet transfers a lot of its energy into the surrounding circumburst medium. And this transfer of energy gives rise to what we call a cocoon of emission. And when this cocoon breaks out of the material, because this cocoon is only mildly relativistic, so Lorentz factor of 2 to 3 instead of a Lorentz factor of 100, and it's very, very wide angle, it can easily explain the low luminosity in the gamma rays. It can explain the time lag between the merger and the subsequent burst of gamma rays. It can explain this long wait to see the radio and X-ray emission. Furthermore, this cocoon, because it's accelerating all this heavy elements and all this material here, this acceleration just by Doppler effects can explain, as one of the ideas to explain the early blue emission. And I hope Dan will give you yet another idea to explain that early blue emission that was somewhat of a surprise. It was a little bit too uncomfortably bright, I would say. And the model works. It can explain the bolometric luminosity as a function of time, the temperature as a function of time, velocities are a few tenths the speed of light of the ejector, that velocity is a function of time, radius. One thing that remained an open question, at least on October 16th, was what is the fate of the jet? Did the jet get completely choked by this cocoon, or did the jet transfer some of its energy but escape in another direction? So if you had a friend on a different planet that was looking at this from a different line of sight down the barrel of the jet, maybe they would see an ordinary gamma ray burst. The way to answer this question is really the radio and the X-rays, because the speed and the width of the jet versus the cocoon gives a very different signature in these extreme wave bands. And here's a radio light curve as of October 16th. And it was consistent with a very wide off-axis jet as well as possibly a cocoon. Stay tuned, because in just a few days, you'll see a few more points in this light curve, which seems to be very consistent with this idea of a cocoon. Furthermore, you can use a network of radio telescopes around the world to directly measure the size of the ejector. And the size of the ejector is obviously, again, just a function of speed. And here's size relative to the solar system. And just by putting a ruler, you can measure the size and distinguish between an ultra-relativistic jet, on-axis, off-axis, doesn't matter, and a cocoon, which is mildly relativistic and much wider angle. So I'd like to conclude with a NASA animation of how this whole model holds together. It's a cartoon, but it's a fun one. So you can see the neutron stars coming closer, the tidal tails, all the material being spilled out into the surrounding medium, the merger, the jet being launched, the jet being stuck, the cocoon, the blue emission, then quickly becoming red, and then this forward shock that's giving you the radio and the X-rays. And with that, I'd like to hand over to Dan Kaysen, so he can tell you more about what we've learned from this data set.
Thank you, Mansi. So if you have questions based on Mansi's talk, either tweet them to us using the hashtag GWNuclear or by sending email to gwnuclear@nscl.msu. And so like Mansi said, next we're going to hear from Dan Kaysen about interpreting these electromagnetic observations, or more interpretations. So take it away, Dan.
Great, thank you, Luke. So yeah, we've gotten a great sense already about the exciting science that's come out of this event, and I'll tell you a little bit more about one piece of that, which is how the optical and infrared emission can tell us a little bit about this question of the origin of the heavy elements in the universe, and how they may be formed in some significant part in these kind of neutron star merger events. It's one of the long-standing questions in astrophysics, actually, where all the stuff in the universe came from. This plot's showing basically the distribution of elements that we find in our own solar system. And there's a lot of stories to tell. Early in the universe, after the Big Bang, there was really only hydrogen and helium, and everything essentially heavier than that was produced in stars and different kinds of stellar explosions, massive star fusion and core collapse, supernova, thermonuclear white dwarf explosions producing the iron group. But all the elements above the iron group have been one of the big open questions for many years. I've been pretty sure that to make them requires some process of neutron capture, which I'll talk about in a little bit more detail. In some part, a slow neutron capture, in other cases, a rapid neutron capture or an R process. But exactly where this R process event happened in the universe has been one of the big questions for many years. Is it something in supernova? Does it involve neutron star mergers or some other sort of event? And you can see these are very, above iron is a very small fraction of the total amount of elements in the universe. But they're a very interesting fraction. I mean, this includes all the precious metals like gold and platinum, radioactive isotopes like uranium, and rare earth elements, and a lot of other interesting things. So, in the past, we've been basically relying on the fossil record of those heavy elements to try to decipher their origin. Now, with this new event, we had a chance to see some of that material being made in its site in one of these neutron star mergers. And a lot of this, before that, was based upon theoretical ideas of how material might get ejected in a neutron star merger. Monty showed a nice simulation at the end, which was really just a cartoon picture, but you can actually calculate the merger physics in some detail by trying to model the relevant physics involved, and that involves a suite of physics, really. Hydrodynamics, so these two stars coming together, some information on the nuclear equation of state that Jocelyn will tell us more about, a treatment of gravity, general relativity, neutrino physics, and nuclear reactions, which all go into the picture. And of course, it's hard to put all that into one single simulation. So most of the calculations are done using high performance computing, but still approximating some of the physics involved. But I'll show you one example here. This is a simulation by Stefan Roswag showing a calculation of two neutron stars coming together. And you see them basically starting to merge together into one merged object, but you also see some material getting flung out in the merger itself. So most of the mass, more than 90%, is going into that central object, which could be a massive neutron star, but it is likely to collapse into a black hole. Whether it does so depends upon some physics that we don't fully understand, really how massive a neutron star can be before it collapses into a black hole. And that depends upon the equation of state and some other physics that we hope to learn more about. But in any case, you see there's maybe a few percent of the material is just flung out of the system. Maybe another few percent or up to 10% is in a disk that more gradually accretes onto the central object and may have something to do with the gamma ray burst that Monty talked about. So just a little more detail about how you might get stuff flung out in a neutron star merger, which will eventually lead to the optical infrared light that we think that we have seen now. There's three different ways, in essence, of how you can do that. In the merger itself, like you just saw, you can have material that's flung out just dynamically. This will be flung out at a few tenths of the speed of light, 0.2 to 0.3 C. It'll be cold, very neutron rich, maybe 10 neutrons per every proton or more. And that's because you're basically just taking pieces of neutron star and flinging them out into space. But there's another way you can fling out matter in the merger itself, and that's as those two stars collide together. There's a shock at the interface, and you can squeeze out material from that shock into the polar regions. And that material will be hotter because of the shock, and it'll be less neutron rich because there'll be weak interactions, neutrino interactions that can change neutrons into protons, and you get something somewhat less neutron rich, which has a big impact on the kind of elements that get produced from that material. And then after the merger, seconds afterwards, so a longer time scale, you have this disk that's accreting onto the central object, maybe powering the gamma ray burst. But some of that material in the disk can also be blown away in winds. And you can actually get a lot of material coming out after the merger itself, maybe even more material than during the merger itself. And that will be moving a little bit slower, maybe less than a tenth the speed of light. And it'll be hot and maybe have a range of neutron richness. So what becomes of this stuff that you fling out in this neutron star collision? I'll show you sort of a cartoon picture and then show you some more detailed equations, calculations. So the basic idea goes back to work by Jim Latimer, who's on the panel here today, that when you fling out material from a neutron star, originally it may be quite exotic inside the neutron star, but it probably quickly, as it decomposes into free nucleons, neutrons and protons. And we expect more neutrons than protons in this environment. And then as it expands and cools, the neutrons and protons will combine into to alpha particles, helium nuclei. And so you'll have some of those with some excess neutrons left around. Those alpha particles will then fuse together into heavier nuclei we call seeds. So these probably go up to maybe the iron group, but not too much beyond that before you stop being able to fuse. And then the process that goes on from there is this process of neutron capture, where neutrons bombard these seeds and stick to it, and you grow to heavier and heavier nuclei. In that process, neutrons afterwards beta decay to protons, and you build up nuclei that way. And so the more neutrons you have per seed, the heavier you can build up your elements. Here's a more detailed calculation of that process, this R process. This is work with by Jonas Lippener and Luke Roberts, our moderator. Here's a chart of the nuclei. So basically all the nuclei we think that can exist in nature, and the number of protons and the number of neutrons. And the square boxes you see there are the stable nuclei that we see around us. And so this calculation shows the flow that I just cartooned in the last slide of nuclei. This is starting from some seed nuclei, shown in red there, around the iron group, and then progressively as we capture neutrons and then beta decay to protons, this flow builds up very far from the region of stability. It builds up to the very heaviest elements, where it may fission and cycle back down. But in a process of a few seconds, it builds up into these heavy elements, and then it may take days, weeks, months for it to decay back down to stability, as you see here. So one of the key issues in trying to understand this flow and how these elements are formed is the nuclear physics of what the rates are for different processes in that flow, what the masses are of the nuclei. And since all this happens very far from stability from the nuclei we easily have in the lab, it's hard to know much about that exotic region away from nuclear stability. And so that's done in various accelerator experiments, and you can see here in this plot showing the same chart of the nuclei. The colored regions showing regions that we know something about, but what we'd really like to know is the properties very far from stability. And so that's what various experiments are working on, including the facility for rare isotope beams being built at Michigan State is going to try to get us information on that red region all the way out into this very neutron-rich region far from stability. And that'll make a huge difference in our understanding of how those heavy elements build up and how we can understand and extrapolate even to further regions away from stability. So what you get out of those calculations in terms of the abundance of elements produced, it depends both upon those nuclear inputs and upon the conditions that you have in the ejected material from the neutron star merger. So at the top, it's showing you basically a calculation of the distribution of elements of different masses. Each of these colored lines is a different theoretical model of what the properties are of those very unstable nuclei. And you can see there's some robust features in terms of the peaks in the mass abundance distribution. But there's some significant differences, in particular at the very heavy end, how much material you make and the distributions in between. And those can have important impacts on what we see from the neutron star merger and its aftermath in this kilonova mission. And then the bottom plot showing you how important the conditions in the ejecta are in determining what gets made. The red and black lines are material that were ejected and was very neutron rich, so it built up into heavy elements, basically stuff heavier than A of 130. The cyan line is material that was less neutron rich. And it only made it up to maybe A of 130, but was mostly producing nuclei in the in-between regions. And so here's kind of a schematic picture that's trying to synthesize maybe hundreds of papers of work around the world of people trying to simulate these mergers and their nucleosynthesis. And you get a generic picture that might look something like this, where in the equator you have these tidal tail ejecta, which is neutron rich and produces very heavy R process nuclei. While in the poles, you may have this squeezed hotter material that is less neutron rich and makes only lighter nuclei. And then there may be some wind moving more slowly coming from that region around the merged remnant that produces maybe a range of different nuclei depending upon the conditions there. So that's theoretical ideas, but what's amazing is now with this new event, we can actually see directly and probe that material that got ejected. And that's the idea going back to Liam Pachinski, and also revived by Brian Metzger and Luke Roberts, that the material here is radioactive that gets ejected, and we can see that glow. So originally the material is quite compact, but it expands rapidly. It's moving at a few tenths of the speed of light. After about a day, it's grown from neutron star scales all the way out to something the size of the solar system. So you have a very tenuous cloud there of material, and it's highly radioactive. These are these unstable neutron-rich nuclei that are beta decaying back down to stability. If you have some of the heaviest trans-lead nuclei, you can have significant fission and alpha decay. If there's free neutrons, you can have neutron decay. All of these processes are going on and heating up this big radioactive cloud, which is going to be radiating at something like 10 million times the luminosity of the sun just from its radioactive glow. That brightness is about 1,000 times the brightness of a nova in our own galaxy. So that's what coined this term kilonova. It's somewhat bright, but it's compared to a supernova, which we see more often, it's maybe 10 or 100 times dimmer. So it is quite difficult to find. And the temperature is somewhere around 5,000 Kelvin, or something not so far away from the temperature of the sun. So it's radiating visible light and infrared light. And so from that physics, you can model actually what we think the light curves and the spectra of these events should be. Here's some calculations done with Jennifer Barnes showing that what we see is actually quite dependent upon what the composition of the material is. So the red line here on the left showing you a light curve if the material is made out of the heavier R process elements. And for atomic physics reasons, that material is quite opaque, and we get a very long-lived, maybe a week-long transient due to the long time it takes photons to diffuse out of this very opaque cloud of debris. Whereas if you have light R process elements, you get something that's somewhat brighter and briefer because the opacities are significantly lower. And that plays out significantly in terms of the colors of the spectrum that you see. If you have these heavy elements, the optical regions are blanketed and you see most of the emission in the infrared. If you have lighter elements, you see most of the emission coming out in the optical. So the color and the time scale of the emission that Monty talked about is sort of a direct probe of the composition that we're seeing. And Monty showed some comparisons. Here's just a simple picture of what we think we might be seeing in the data that she and others took. At early times, we're probably seeing mostly maybe the squeezed polar material that's lighter, maybe 2% of the solar mass of that, that's producing mostly short-lived blue emission that fades away quickly. And then at later epochs, we may be seeing heavier elements that give us a redder emission that lasts for longer, in a few weeks or so. And in that way, you can provide reasonable fits to the color and brightness of the event we see. One can ask, what in more detail, what are we seeing here? Monty showed a comparison of a spectrum. Here's another comparison of the observed infrared spectrum to one of our models, and you can see some agreement there. One would like to go further and try to extract details about what the composition is of the material in detail. That's hard to do because the features that you're seeing here, the undulations, are not from any one specific element. They're really a blend of lines from many, many different elements. But there's still information to be teased out of here. As you change the abundances, you change the locations of these peaks. And so we're starting a new era where we're going to have to learn how to spectroscopically analyze this material and pull out details about what exactly that we're seeing. So this was a really exciting event. It was really the first time we were able to probe and directly measure the amount of heavy elements produced in an event. And it's really the first time we've confidently or fairly confidently been able to say we've seen the production of R process elements. And you can ask if there were enough R process elements to explain everything that we see in the galaxy. And there's uncertainties in terms of the rates that Duncan mentioned and in terms of the masses ejected. But basically, as a back of the envelope calculation, there was enough material produced to explain the bulk of the heavy R process made in the universe. But as we hopefully see many, many more of these events and get both gravitational waves and electromagnetic data, we'll have a better sense of what's going on. And I expect that we'll see diversity because the material that you eject depends upon several things: the mass of the stars involved, whether they're neutron stars or black holes, what the equation of state that Jocelyn will tell us about is, and again, those nuclear physics inputs. So we may get a range of different behaviors that we can start to understand with a different sample of objects. And as you can imagine, the ejected material is not quite symmetric. So as we look at these events from different viewing angles, we might expect to see different amounts of emission depending on which way we're looking. And what's incredible is that with the gravitational wave data, we get some information about what the orientation is of the system. So we can virtually fly around these kilonova and look at them from different points of view. We get information about what the masses are as well, and we can start to put together a detailed picture. So I'll just leave with kind of this general sense of what's going on here. It's kind of remarkable on the theory side. We're connecting physics across all these different scales, all the way from the nuclear subatomic scale to the stellar scale of mergers to the galactic scale of the formation of elements. And then we're in a special time where we have these amazing facilities that are probing nature on all those scales. The FRIB probing what's happening on the nuclear scale, LIGO and astronomical surveys probing the merger scale and the production of elements. So it's really just the start of an exciting time, and it should be really interesting to see what happens in the years to come.
Excellent, thanks, Dan. If people have questions for Dan, and if you're just joining us now, you can ask questions via Twitter using the hashtag GWNuclear or using the email address gwnuclear@nscl.msu.edu. So the kilonova and R process production is one sort of very exciting aspect of this event. But the other exciting aspect for nuclear physics is also what we can learn about neutron stars themselves from this event. So our next speaker is going to be Jocelyn Reed at Cal State Fullerton, and she's going to tell us about what we can learn about the properties of neutron stars from this gravitational wave signal. So thanks for coming, Jocelyn, and take it away.
Thank you very much. It's really great to be here this morning. So let me just set up my slides, and as I prepare, so I'll give you a picture of what we're learning about this event from the gravitational wave side of things itself. So mapping from the data shown in the bright green curve here that Duncan talked about earlier, back to the properties of the source itself, the binary neutron star merger seen in the top left. So just to set the scale for those that might have been joining, compared to something like our black hole mergers that we've observed already in gravitational waves, this is an observation of a different scale, order of 100 seconds visible in the gravitational wave data, but not visible by eye per se, but compatible with our analysis algorithms. So over thousands of cycles of the two neutron stars orbiting around each other, stirring up the gravitational waves and measuring that evolution in their frequency over time, we are able to infer the properties of the component stars that generated the gravitational wave signal. So this, as Duncan said, tells us some things about the masses and spins of the component stars. So this is just the mass of the more massive component and the less massive component. We very precisely measure a combination of these masses, the Chert mass, and then we find that this is compatible with an equal mass system of very typical neutron star masses seen in galactic observations. But due to some degeneracies in the gravitational wave signal between the mass ratio and the spins of the signals, we have a lot of uncertainty in the exact values of the component masses. So we can make some astrophysical assumptions about the spin of the stars. This is a low spin system compared to the binary black holes we've observed. If we restrict to quite small spins, which is indicated by the blue in this plot, we get mass ratios that tighten up closer to the equal mass system one might expect from looking at neutron stars in our own galaxy. But what I really want to talk about mostly today is using this gravitational wave observation as a sort of an astrophysical scale collider that will tell us about the dynamics of these two dense objects as they approach each other and even before they collide. And that allows us to probe sort of the phase space of dense matter in a different way than most of our earthbound collisions can give us access to. So neutron stars are not sensitive to temperature when they're isolated after they've cooled from their initial formation. They're relatively cold. We expect them to be in equilibrium. So that's probing a cold, dense matter region of the parameter space until they collide, in which case that dramatic event can increase the temperature and start to give some hints of other aspects of dense matter physics. But as Dan introduced, most of what I'll be talking about that we learn from observing the dynamics through the gravitational wave signal is the properties of dense matter in beta equilibrium, the cold equation of state at and above nuclear density that determines the properties of the neutron stars. So given a mass of a neutron star, this tells us the radius, the deformability of the star, and also leads to the maximum stable mass that determines some of those final fates of whatever merged object was produced by this signal. So to look at the impact of matter on a gravitational wave, you can start with the gravitational waveforms stirred up by just 2 point particles, things that do not have matter scale, a radius that's significant, more similar to what we see for black holes. And it turns out that most of the in-spiral, so this central panel here is just zooming in on the last 2 seconds of that order 100-second signal recorded by the gravitational wave detectors, starting around 2 seconds before merger, when the objects would be roughly sort of 100 kilometers apart, orbiting each other orbiting each other 50 times a second. And then over the last seconds, they fall together, orbit more quickly, and then the final fractions of the second, you see this more characteristic chirp pattern as the stars collide. Now, if I try to put matter in this scenario, the first thing we'll notice is that looking at sort of the top panel, the early in-spiral dynamics are primarily determined by the masses and spins, and those are going to be very hard to modify. But the final fraction of a second will be modified if I introduce the differences when the neutron stars have a finite size that modifies their interaction. So I'm going to add in matter to the bottom panel now, and there'll be 2 effects. So the first thing is that at the start of that bottom panel, there's a small shift. The tidal interactions of the stars have led to an accumulated phase shift at the higher frequencies. And then the final stages of the merger are driven primarily by their matter effects. The stars eventually crash together at a frequency that's very sensitive to how large they were. That limits how far they can fall in. So what we're going to do is use these properties of the neutron stars to map back to the dense matter that generated them. So there's sort of 2 features, and this in-spiral effect is actually what we have so far used to learn about neutron stars from the August detection. So as the stars deform each other through tidal interactions, that takes energy away from their in-spiral and accelerates them towards merger. the size of this effect is determined by a combination of the radius, the size of the stars to the fifth power. So this is a radius interaction that becomes very significant when the size of the stars approaches the size of their orbital separation. And there's also a love number, this K2 here in this formula presented, which can be considered a reflection of how centrally condensed the stars are, which will affect how deformable a star of a given radius is, how much the tidal interaction changes the gravitational potential. And so on the bottom, we see this equation of state of cold dense matter above nuclear density with different pressure scales. As the pressure increases, the radius of the neutron star increases, and the acceleration of the in-spiral shifts the merger to earlier times. Now this green scenario here is quite an extreme scenario, and that's actually going to be disfavored by our data analysis of the neutron star merger. So just to close the picture in terms of what I'll talk about today, if we compare the merger of compact stars, which I'll start on the top panel, these are going to be stars starting at roughly the same separation. The top panel is more compact stars, the lower panel is larger radius stars. The larger radius stars are already hinting at tidal deformation, you may be able to see in this panel. And just focusing in on their final orbits and merger, we'll see that the large radius stars deform more, accelerate their in-spiral, they collide while the compact stars can still orbit. And so the merger happens a little earlier. Now these demonstrations are also showing some variety of scenarios for after the stars collide, whether they collapse to a black hole promptly, whether they live as some sort of hypermassive object before a collapse. It's also possible that they could have had a long-lived neutron star remnant. That's, at least in terms of the gravitational wave data, not visible because the high frequencies of a post-merger signal are hidden by the detector noise, although this may, with future upgrades to the detectors, no longer be true. So what does this tell us for the particular observation? So I'm showing a plot from our discovery paper where we talk about the component stars, the smaller star and the larger star, and a measure of how deformable each star is, with a particular assumption that the spin is not so large, and a waveform model that we've determined is actually recovers reasonable parameters, even though it's quite a simple waveform model when compared with more sophisticated analyses. So we allow the deformability of each of these stars to vary. We see which parameter values best match the data in concert with the variations of the masses and spins. And we see that 170817 supports lower deformability stars with a 90% limit in this sort of diagonal line. The two deformabilities are the properties recovered are correlated in their impact on the gravitational waveform. So similar to a chirp mass, you can consider sort of a chirp lambda that maps along these contours here of how we recover the properties of the stars. Now, we can compare these to equation of state predictions generated by taking the recovered masses of the in-spiral, applying an equation of state that maps those masses to the deformabilities compatible with that, starting with the equal mass case, where the deformabilities are equal, and sweeping up with the mass ratio of the two different stars. And this shows that some equations of state are over all ranges of the masses we consider distinct from our supported region. It's also worth noting that we can't confirm here from the gravitational wave signal alone that the stars are not more compact than neutron stars might be expected to be. We have so far only upper limits on the size of the star, which increases their deformability or has a less compact star. But roughly, we can map these equations of state to the radius of their associated stars and sort of the equal mass limit. And we see that the 90% limit is roughly along an equation of state that gives order 14-kilometer radius for the neutron stars. So we're supporting more compact neutron stars with this observation. And some work by the LIGO and Virgo collaborations continues to reanalyze the data of this same gravitational wave signal with some careful systematic estimates and linking the properties of the stars with equation of state assumptions. And so we think we may be able to say more in future with this ongoing analysis. So I'll wrap up with exciting thoughts about where we might be going in future with this. So as Duncan mentioned in the first talk, this first observation has hinted that neutron star mergers are not rare, that, for example, in a year of observation, we might get order 40 events. And with advanced LIGO's design sensitivity, that would lead to an equation of state constraint that here on this left panel is sort of an injected equation of state, say, for this family of recovered events. And then this blue contour here is a 95% confidence region on that equation of state that is separating it from other equation of state candidates that only have relatively small variation in the overall pressure predicted by the equation of state. On the right panel is an implication for radius constraint implied by this combination of gravitational wave observations alone. So we're hopefully in concert with other equation of state implications like those that Dan talked about, where you can sort of infer again from the equation of state how much matter might have been injected and its properties through careful numerical simulation. And of course, the whole other array of neutron star observations in progress. We could be entering an exciting era of precision nuclear physics on the astrophysical side too. So hopefully we'll now hear from some other folks about how that translates into the nuclear physics side of things.
Excellent. Thank you, Jocelyn. Yeah, so if you have any, we've gotten a couple of questions for Jocelyn during the talk, but if you have any more, please tweet them to us at the hashtag GWNuclear or email them to us at gwnuclear@nscl.msu.edu. So next, we're going to hear from Artemis Spirou here at Michigan State University about opportunities for terrestrial experiments that can help us to understand the properties of these events, in particular our process and maybe nuclear equation of state. So take it away, Artemis.
Thanks, Luke. Thanks, everyone. I'm really excited to be here. So my plan for the next few minutes is to try and dive deeper into the details of the nuclear physics and try to show a little bit of which nuclear properties are more important to help us interpret better these observations of the neutron star merger event. So I'll start with the same movie that Dan showed before, but I want to focus a little bit on a different aspect on the nuclear physics properties here. So as Dan mentioned, the boxes here at the center are where the stable isotopes are. And then there are a few lines on this plot that correspond to what we call shell closures, or we also call them magic numbers. So for the non-experts, these magic numbers, if a nucleus has let's say a magic neutron number, it means that it wants to keep that neutron number, and it doesn't want to, it doesn't want to change it to add more neutrons or remove more neutrons. So this is a basic nuclear physics property. And it's amazing how this connects and affects the abundances that we see around us all over the universe. So let me start the movie here, and you can, as the flow, our process flow goes up, you can see how matter accumulates as soon as it meets one of these magic numbers, and then heavier into this other magic number. So you see the more intense regions where just exactly because of the property of these magic numbers, you tend to accumulate more matter. And that then later in the decay, after the decay happens, this translates into the peaks that we see in the abundance distribution. So this is just an amazing connection, a one-to-one connection between the basic nuclear physics properties and what we see in the stellar observations. And this is exactly what I want to focus on for the rest of the talk. Another thing I wanted to point out here is Dan mentioned the two components that were observed in the new discovery, and there was a blue component that was more on the lighter elements, and there was also a red component that showed up with heavier elements. Oh. Okay, there we go. Yeah, so if I put those components on this chart of nuclei, again, we know where to focus on, and the exact extent of these circles can be a little bit different. But the main point, as Dan mentioned as well, is that when we see these components, we don't know exactly the contribution of the different elements in the distributions. So in order to model and interpret what we see in the observations, we really need to go deeper and understand the nuclear physics properties that go into these calculations. So let's take a quick look. This is a cartoon version just for the non-experts to understand a little bit of what kind of nuclear properties are we talking about. So I'm zooming into part of the chart of nuclei and then zooming further into, let's say, an art process path, where the main things that are happening are either a neutron capture, like Dan mentioned before, that would move this way, or you could have a beta decay that would move this way. This is the most basic competition here between the two kinds of reactions. And so depending on which one wins, the reaction flow will take a different direction. Now, of course, this is the simplest case. You could also have beta delayed neutron emission, which means that you move one nucleus over, one less neutron rich. This process enriches the environment more in neutrons because it emits neutrons, and it also ends up in a different nucleus. So when you decay back to stability, you will end up at a different mass. Another important thing here is that you could also have gamma end reactions, so the inverse of the end gamma, and this happens if the environment is very hot. So for the two components that Dan has been talking about, one is a hot environment and the other one is cold. So for the hot environment, you would expect to have a gamma end gamma equilibrium, but for a cold environment, this might not be the case, in which case the neutron captures become even more important. So let's look a little bit closer or more all these properties. So the properties I mentioned already are listed here at the top. So we have we need to know beta decay properties. We need to know neutron captures. As part of all of this, the masses are very important of all these nuclei. And then I didn't talk about it earlier, but fission is very important. Fission properties, neutrino interaction rates, and of course the equation of state. So we need to know all of this. Let's see a little bit about what we know already. So the chart of nuclei shown here has kind of, again, a simplistic art process path. And then the reddish color shows how far we can reach, or we've already reached with current facilities. So these are the measurements of masses and half-lives of nuclei that we can do right now, or we've done already right now. And you can see that we are touching a little bit on the art process path in some regions, but for the most part, we're not really there yet. We're not reaching the whole art process path yet. And this line that's kind of hidden on the back here is where the next generation facilities are going to reach, FRIP, and I'll talk more about FRIP later. I just wanted to point out that with FRIP, we will be able to reach almost all nuclei involved in the art process. Okay, so we don't have data right now for this nuclei, but maybe we can do good enough with theoretical calculations. So let's see if this is the case. Well, the short answer is no. We really need data. And to show that, I have just 3 examples here. At the top corner, I have masses. It's 3 different mass models. I'm not going to go into the details. But what that picture shows you is that in the region here where you do have data on masses, measured masses, the different models agree with each other. But as soon as you go further away from the known data, then the models just diverge. And so it's impossible to know if I should use this model for my process calculations or if I should use this model. And it's really important to do these measurements to get experimental data. Similar stories for the neutron captures. Chart of nuclei here, the color code is, again, this diversity, this variation between the model predictions, and the red color is a factor of 100. So again, very quickly, you can see that we get to factors of 100 or even more uncertainty in these predictions. And very similar for the half-lives as well. So it's important, we clearly don't have a very good understanding of these properties. Let's see how this affects the abundance calculations. Now, with the neutron star merger observation, this is now great because we don't have to run the 50 or 100 different scenarios and figure out for each of them which nuclei are more important or what is the impact. We can now focus on this one, the neutron merger scenario. And this doesn't mean that this is the only scenario that can contribute, but at least with this one, we have very good observations and we can constrain much better. So the two plots here show the top one is for varying the masses of nuclei within the theoretical uncertainties. And then the bottom one is varying the neutron captures, again, within the theoretical, those variations. And so what you can see is that the abundance predictions coming out of varying the masses and the neutron captures is quite a broad band. So we don't have a very good handle of these predictions unless we narrow those bands down. And we can only do that with getting more experimental information. So we need more data. That's the main message. But there's thousands of nuclei involved in this in the R process, and we don't expect to be able to measure every single one of them. So we really have to focus on identifying the most important ones. And this is done already using sensitivity studies. These particular sensitivity studies for neutron capture rates for a neutron star merger scenario, and the darker the color, the more important that neutron capture is. And so you can see that it's not everything. We don't need to measure everything. We can focus on particular regions where these neutron captures matter more. And the other amazing thing is that if you see the black line, which is how the FRIB reach that we expect, all of these important nuclei are within FRIB reach. So we're really excited when we can do these measurements with FRIB. Okay, so we are already very busy running experiments. We're not just sitting around waiting for FRIB. There's a lot of measurements already happening around the world at many facilities where we're measuring important R process properties. And I'll just show you a few examples. I can't show everything, but I'll just give you a flavor of what's known, what's measured. So for example, here I have Argonne National Lab at the Caribou facility. They did a lot of work measuring masses. So we have a lot of new masses from those experiments. And at the Riken facility in Japan, they did a lot of work measuring new half-lives. Now, these two quantities are quantities that we can measure directly. If I want the half-life of a nucleus, as long as my facility can provide that beam, I can go and measure this property directly. This is not the case for all properties, however. The most difficult one is neutron captures. Even if I do have the beam available at my facility, I still can't go and measure directly the neutron capture just because I can't make a target out of that short-lived radioactive nucleus, and I can't make a target out of a neutron. It's a pure technical difficulty, but it's a very important one because we just cannot measure these reactions directly. But we're, again, trying to figure out solutions to this problem. So instead of measuring these reactions directly, we're figuring out ways to get information and get them indirectly. So there's at least two indirect techniques that, especially in the last few years, they've been developed a lot. One is it's called the Surrogate Technique. And this is simply, it's shown in this graphic here, where instead of getting a neutron captured on your nucleus A here, we can use a deuteron that I can make a target out of, and then I shoot that deuteron on my target nucleus, and now I kind of sneak in that neutron into the nucleus nucleus and the proton just flies away. So this way I kind of simulate a neutron capture, even though that's not exactly what I'm doing. So this is the surrogate approach. Another approach that it's actually my group here at MSU in collaboration with the University of Oslo. We are doing measurements of just measuring basic nuclear physics properties of the compound nucleus that you would expect from a neutron capture, and we use beta decay to populate this nucleus. So again, instead of measuring the neutron capture directly, if I learn enough about the system, I can go and constrain the neutron capture, and we can put pretty strong constraints on these reactions with both techniques. So as you can see, we're already busy developing techniques and developing equipment with current facilities. But what we're all especially excited about is with the next generation facility, which will give us access to exactly the right isotopes for our process. So facility for rare isotope beams, we've heard already a lot about it through almost all talks. So it's a project that's funded by the DOE Office of Science, and it's being built here at Michigan State University. The plan is for the facility to be completed in 2022, although we're all hoping that it will be ready even earlier. And there's a large community of users from all over the world that's already engaged and getting ready to use this facility for experiments. Let me show you a little bit of how, again, a cartoon version of how this facility works, how we can do experiments with it. So at the bottom here, we start with our stable beam. That's how you start. And that gets accelerated through the FRIB accelerator to about 200 MeV per nucleon. Then it hits a target, and it has where we have a fragmentation reaction. That means it literally just breaks into pieces. And most of these pieces will be radioactive, and it's these radioactive rare isotopes that we're looking for. Now, we don't want to use all the pieces, all these fragments that are coming out. We only want to use one of them, the one that we care about. So we use fragment separators to separate out the isotopes we don't need, and then focus and use the ones that we do need. And we can do experiments using these isotopes that are moving very fast. Or we can also stop them or slow them down very much and do experiments like mass measurements and laser spectroscopy with these slow beams. And finally, we can also reaccelerate them to astrophysical energies and do experiments with those beams as well. Now, FRIB is not just created out of vacuum. It's built on 50 years of experience with rare isotope beams that is already there with the current facility, the NSCL, National Superconducting Cyclotron Lab. And as you can see here, the NSCL already exists, and it feeds beams into all of these experimental areas. And when FRIB comes online, we will be able to use all the existing equipment on day one to do experiments. And of course, we're developing new equipment as well. So just to get an idea of some of the equipment used for our process measurements, I'm showing here just pictures, and I'm not going to explain them individually, but just to get, again, an idea of all the diversity of equipment we use to do this kind of measurements, to measure masses or measure beta decay properties or neutron captures. So to conclude, we're really excited about the recent gravitational wave discovery with the neutron star merger event, because it opens new opportunities for nuclear science. So it will help us understand all with nuclear data, new nuclear data, we'll be able to understand better the different contributions of elements for this blue component and the red component we talked about already. We're already running experiments at current facilities, but we're all really excited to be ready to run experiments at FRIB, either with the existing equipment that's already available. We're also building new equipment, of course, that will be ready for FRIB experiments. So that's it. Thank you.
Thanks very much, Artemis. So if anybody has any more questions for Artemis or any of the other speakers, you can ask those through Twitter using our hashtag GWNuclear, or through email, which is gwnuclear@nscl.msu.edu. Okay, so those are all the talks. And so thanks to everybody for the very nice talks that's sort of giving us an overview of what was observed and maybe how to interpret some of those observations from GW 170817. And the next part of the event is really going to be a panel discussion that's going to involve a few other people who we haven't heard from yet. And so before we get into answering all the questions that we've gotten during the talks, we're going to give everyone on the panel a few minutes to sort of give their perspectives on this event and what it sort of may mean for nuclear science going forward, what interesting questions are out there, those sorts of things. So the first panelist that we're going to hear from is Jim Latimer at Suny Stony Brook. And so among other things, Jim is one of the originators of the idea that our process nuclei might be synthesized and material ejected from these mergers. So welcome, Jim.
Okay, thank you. It's a pleasure to be here. This event has really been very exciting for me. As you've mentioned, my thesis advisor was David Schramm, and he had proposed originally this idea, showing a great deal of prescience, I think, in this suggestion. If I can just flash up a picture here. So as I said, Dave had proposed this idea that we investigate neutron star mergers with the idea as to looking for the origin of the R process. And we did some simple calculations, but we used black holes instead of neutron stars. Well, we merged black holes with neutron stars because we thought that was a simpler problem. But we found essentially the idea that matter would be ejected and that it would probably form R process nuclei. But for many, many years, of course, this idea was put in the background compared to the idea that the real source of the R process was supernovae. And it's only been in recent years that the picture has turned around. So this event has really been fantastic in showing that this original idea might in fact be correct. The other interest I have in this event is its impact on determining the neutron star equation of state. And I think from this there are two aspects. One is determining neutron star radii, and the other is determining new limits on the neutron star maximum mass. And as Jocelyn has mentioned, and according to the analysis that I've been working on, I think the upper limit to the neutron star radius is more or less around 13.5 kilometers from the data that we have. And in addition, if one assumes that a black hole was made in this event, which most models showing large amounts of mass ejection are usually accompanied by black hole formation. Also, the appearance of the gamma ray burst suggests that a black hole formed fairly quickly. From that assumption, you can determine that the upper limit to the neutron star maximum mass is around in the range of 2.4 to 2.5 solar masses, which is a much better number than we've had before. And there are several papers also suggesting, Andreas Bauswein is on one of them, suggesting that we can also set lower limits to the maximum mass. Brian Metzger is another person who's been interested in this. Set a lower limit to the maximum mass in the range of 2.1 to 2.2 solar masses. And that's above the current lower limit that we have presently. So in all, this event has been very exciting. There's a great deal of impact for nuclear physics. Even from the single event, I think we're seeing some interesting limits being made. And if Jocelyn's right and we get dozens of events per year, we're really going to be much better off from determining about the nuclear equation of state. So thank you.
Excellent, thanks, Jim. So the next panelist that I'd like to introduce is Ani Abrahamian from the University of Notre Dame, who's a nuclear experimentalist who's worked on measuring the properties of nuclei in and near the R process path. So welcome, and we'd definitely also like to hear your perspective. So.
Thank you, Luke. Like everyone else in this panel, I'm very excited with this multi-messenger observation. Particularly excited about the electromagnetic spectra that's associated with the gravitational wave measurements. As a nuclear physicist, I have been, or I should say my research focus recently had been on measuring nuclei and measuring nuclear properties and using the observed abundances of the heavy elements to try and distinguish between astrophysical models for the site that might be responsible for the production of the heavy elements. Now that we have a definite site perhaps not the only one, but a definite site with the merger and the associated signatures. I feel that now that gives us a little more impetus to our measurements of these very neutron-rich exotic nuclei, particularly because they will give us a glimpse into what's happening inside the merger. My theory colleagues here at Notre Dame have done some work in reverse engineering nuclear models along with what is known, and they were actually able to tease out differences between different neutron star merger trajectories. So I was very excited to hear from Jocelyn about some of the variations or surprises that they got with this observation. And I think it might just be possible that we can use the nuclear physics or the properties of these nuclei to basically tease out the details of what's happening inside. So that's a very exciting prospect for me and my collaborators. So we've been measuring some of the very neutron-rich nuclei at the Canadian Penning Trap facility at Argonne. And in fact, some of these have been the most neutron-rich measurements that we can get our hands on. And of course, we're also planning on using FRIB in the near future to continue some of these measurements. It's exciting that the neutron-rich nuclei or the production of these very exotic things are very important for nuclear physics for itself, but it might also here provide some hints, a real glimpse into what's happening inside the merger. So thank you.
Thanks, Anya. Welcome. So our next panelist is Andreas Bauswein at the Heidelberg Institute for Theoretical Studies. And he's worked a lot on modeling neutron star mergers. And so he's going to also give us some perspectives about what this means and what the way forward is. So welcome, Andy. Oh, sorry, I muted you.
So I think what I would like to point out is that I find it really amazing how much we already learned from this one single event. I mean, how much we learned, for instance, about the R process from the electromagnetic counterpart, but also what we in particular learned about the nuclear equation of state, that we can really have already some constraints on the nuclear equation of state. Of course, some of these constraints are maybe, let's say, a little bit more tentative, others are more quantitative and more robust. And of course, it's a task for the future to somehow order all these different types of constraints and to arrive at a consistent picture of what we actually really know about the nuclear equation of state. But I think overall, we can conclude that we are really approaching a point where we get a much, much better idea of what is the actual possible range of the nuclear equation of state. Of course, most of these constraints and conclusions in one way or the other rely on numerical modeling, and it's also clear that to some extent these models still need to improve and that there's still a lot of work to do to solidify the models and the numbers. And we should keep in mind that in particular when we speak about the ejector and the R process, we still deal with a number of uncertainties from the hydrodynamical models. But overall, I think it's reassuring that the overall picture, that the ballpark of numbers more or less agree with each other, although there's still some work to do. And this brings me to my wish list for the nuclear physics community to, let's say, future research opportunity. At least from my perspective as a modeler of mergers, I think what we really need is to get more equation of state models. So, I mean, in particular, models which contain the temperature dependence and the composition dependence. And my point is that I think there are actually only a few models which are compatible with all constraints that we have at the moment, in particular with these new constraints from these recent detections. I think we have a much better idea from the astrophysical point of view, what are the stellar properties of neutron stars, but we also have some constraints from nuclear physics, for instance, about the symmetry energy and compressibility and so on. And I think it would be really helpful if we had a larger set of models which are compatible with all these constraints. And I think what we need are systematic variations of the equation of state models to work out systematic dependencies, because we need these systematic dependencies to interpret future observations, because we should expect that we actually obtain in the near future a lot of more observations, and we will get much more data. And if we want to interpret these data, we really rely on a systematic approach here. And so I think this is my wish to the nuclear physics community, that we get more equations of state which are compatible with what we already know about nuclear physics and about neutron stars. I think this is what I wanted to say. Thank you.
Excellent. Thanks, Andreas. Our final panelist today is Brian Metzger, who's a theorist at Columbia, and he's worked a lot on predicting the properties of the ejecta of these events and what sort of signals you might see from them. So we'd also like to hear your sort of perspectives, Brian, so welcome.
Thanks. Can you hear me? Okay, great. Yeah, I just want to echo what the other panelists have said. This has been an exciting few months working on this event, seeing the implications being played out. Some successes, some mysteries. I think by and large, you know, it's mostly, I mean, it's been a combination of successes, but also realizing sort of, you know, in the future, what we're going to need to turn these into more precise probes of the nuclear physics. So for instance, I think the fact that there was this R-process nuclei, a few percent of the sun's mass produced, is very robust. And I think the fact that, you know, theorists were able to make these predictions for the radioactive heating and the kilonova emission, and then to have it seen, just really puts a lot more confidence in that discovery. And I think this really illustrates, you know, the power and importance of theory, of bringing together, you know, astrophysics and nuclear physics. And so this is, you know, really at the interface of what we need to be continuing to do. As Dan discussed, you know, the colors, the amazing thing is that the colors of the kilonova, which are related to atomic physics, you know, whether their emission is blue or red, is imprinting key information about the nuclear composition in the sense of, you know, whether or not we get past the second R process peak, whether we have matter that is, you know, free or rich in lanthanide and actinide elements. And so that's, I think, the really exciting thing, is that when we see, you know, something that's blue becoming red, or something that's purple, or whatever you want to say in between, you know, how we see this from different angles, we're really sort of, you know, taking an X-ray in some ways of this merger, really learning a lot of the details. You know, but I think it is, you know, important that, you know, for our ability to take a simulation of the merger, what is produced, and to translate it into what we see, there is this crucial step where the nuclear physics comes in, particularly, you know, some of the nuclear properties near these closed shells, which are really determining how far the nuclear flow goes and on what time scale. And so I think there's definitely a key role for facilities like EFRIB to really, you know, improve our ability to make this mapping. I don't know if this was mentioned earlier, but, you know, I think I'm pretty convinced that the dominant source of, you know, the ejecta within these mergers came from the accretion disk that formed around the black hole afterwards, a very large part of the matter. That's at least my opinion. So it's very humbling to think that, you know, the platinum in my wedding band was within a few short shield radii of a black hole, and could as well have just been sucked in as well as ejected into space. So as Jim discussed, I think the other, beyond the R process side of things, I'm very excited about the implications for the equation of state. I think Andy's exactly right. Who would have thought we'd have, you know, from this single event, all of these different constraints coming in terms of the upper limits on the radius from the tidal deformability, the lower limits on the radius from the fact that when these two neutron stars merged, the object didn't immediately collapse into a black hole. We're pretty sure of that. So that, you know, that tells us neutron stars can't be too compact. You know, it's even possible, if the, you know, equation of state can support a very massive neutron star, that when these two things merged, the object wouldn't want to collapse into a black hole. It would produce some very rapidly spinning, highly magnetized neutron star, and we don't see any evidence for that in the data. And so this can begin to constrain the maximum mass of the neutron star quite tightly. So I think a lot of these constraints you'll see from astrophysics, there's, you know, especially these things that are multi-messenger, where we're combining gravitational waves, which measure the total mass of the binary, and then we see something electromagnetically, which tells us about the remnant. they come with systematic uncertainties. A lot of astrophysics does, but that's why it's exciting. We're going to have more of these because we can test some of the ideas. We can say if this is the right explanation, then Y should happen next when we see a merger from a different angle, or if we see a merger with a higher mass, it should do this. And so I think we're going to sort of learn as we go along whether these assumptions we're making are correct. And it'll be fascinating to me if some of the constraints we're getting from these events disagree with those that we infer from laboratory experiments. For instance, like neutron skin thickness of lead or something. If that gives a radius which doesn't agree with what we're inferring from gravitational waves, then what does that imply about the equation of state? Are we seeing some evidence for, not saying this would in particular, but are we seeing evidence for exotic phase transitions that happen in the centers of the objects before or after they merge? So I think that's the main takeaway I want to say, is that it's going to be very exciting as we go ahead to see many of these events, but see slight differences between them, and how how qualitatively different the signals are as we vary the properties of the neutron stars going in will be very fascinating. So I'll finish there.
Excellent. Thanks, Brian. Thanks, everybody. Okay, so during the talks and everything, we've gotten quite a number of questions, both from Twitter and via email, and I think via YouTube. I failed to mention that, but if people are watching this on YouTube, I think you can ask questions there as well. So the first question we got comes from Stan Woosley in Santa Cruz. So this is kind of an interesting question that people haven't touched on so much before, but is whether or not merging neutron stars really can make up all of the R process that we see in our galaxy. So Stan asks, we see that merging neutron stars make elements attributed to the R process possibly in sufficient amounts to explain what we see in the sun. But what can we say about the synthesis of different components? Just like S process, the R process has to be built up from a distribution of exposures, in his words. Is there a need for room for other sources of the R process? So something like supernova to be responsible for maybe the light R process, say less than A of 100. I don't know, maybe either, Brian, do you have?
Well, I mean, I can say just in terms of this event, I think we're seeing evidence for different neutron exposures. We're seeing some evidence for very lanthanide-free matter, which clearly didn't have enough neutrons to get much, past the second peak, and evidence for a smaller fraction that likely did. And so, I guess that's a distinct question from whether the very lightest star process elements come from mergers. Unfortunate aspect of the kilonova is it does tell us, sort of this dichotomy, lanthanides or no lanthanides. But I think we need, to do additional work to really tease out, the detailed quantities of different, isotopes. I think that's, still a little ways off. But my opinion is there, currently there is still room, I think, for the lighter R process elements. But definitely in this event, we're seeing likely a wide range of neutron exposures, and probably a very wide mass distribution being synthesized. But Heather should comment as well.
Yeah, I could say that from the amount of mass ejected, if it's really 1/20th of a solar mass, and most of that goes into our process elements, and given the estimates that the LIGO collaboration has made about the rates, even though there's a factor of 10 uncertainty in that rate, the product of those two numbers gives more than enough R process matter if the sun is a typical, has typical R process abundances.
But maybe it's a little bit too soon to exclude any other contribution. So,
I mean, I think there's some debate going on exactly what the mass fraction of the lanthanides were in this event, and exactly how neutron rich it was. So I think I agree. I think in principle, it seems like we have enough, at face value, but it would be good to see a few more events. And this what we see doesn't really tell us anything about the lighter nuclei. So
yeah. Another question that we have from Mikhail in Scotland and this is maybe best a question for Monsi, is do we have any information about high energy photons produced during this merger, say 100 MeV to 1 GeV to 10 GeV? What is the highest photon energy we succeeded in detecting associated with GW170817?
Photons that were seen. Sorry, can you hear me?
Yeah, I just unmuted you, sorry.
Okay. So the hardest photons that were seen were by the Fermi and Integral satellites. So these were the gamma ray photons. And the NuSTAR satellite still hasn't detected anything. So they're not hard X-rays, they're certainly gamma ray photons that were detected.
Okay. And what were the hardest gamma rays detected, do you know, with Fermi?
I'll have to check the paper.
Okay.
It's probably around, I mean, I'm guessing a few hundred keV or something. I don't think there were too many MeV photons, but you know, we're not talking GeV or hundreds of GeV. So.
Okay. We also got some questions, a number of questions from Indiana. So let me see, where's this question? So one thing that I think a lot of people have asked about, and Chuck Horowitz, this person in particular, has asked about this, is that there's this delay between the gravitational wave or the gravitational waves and the electromagnetic signals. So how should we think about this 1.7 second delay between the merger and the gamma ray bursts? So what could be responsible for this time delay? What might set the delay time scale? What are ideas that are out there for this?
Could I answer this? Okay, I mean, I think broadly speaking, there's sort of four possibilities of maybe increasing interest or probably also decreasing likelihood, but I don't put them in that order. I think, you know, one possibility is that there was a delay between the merger and when the gamma ray burst jet was produced. So this could be because it took 1.7 seconds roughly for the black hole to form and make a jet. It could be that a black hole formed, but it took a long time for the magnetic field or whatever is powering the jet to be produced. It could be that there was a jet produced, but there was a giant cloud of material, which probably Mansi discussed, that the jet had to escape from, and it took a significant amount of time to escape. It could be that the emission site was very far away from the merger, so that the time it took for the light to get from that point to us was you know, there's this additional time delay to get to us from when the gravitational waves did. So that would be like a light, you know, time travel effect local to the source. And then the final one, I guess, would be that there's some exotic physics that's causing gravitational waves to travel, you know, faster, faster than electromagnetic light. So, anyways, but in terms of which is the most plausible, I think it's still up for debate. But I've been increasingly hearing the case that a lot of people believe you do need the jet to be delayed somewhat from when the merger happened. So what would be fascinating is if that was telling us that it took a second for the neutron star to collapse into a black hole, that's sort of an unnatural timescale. We think that what causes the collapse is the removal of differential rotation from the merged object, which is what's supporting it centrifugally against gravity. And most simulations I've seen suggest that should happen quickly within milliseconds or tens of milliseconds, not, you know, thousands of milliseconds. So I think it's still an open question, but a very good one.
Does anyone else have any thoughts on what the implications of this delay might be?
How about you, Luke?
Yeah, I don't have any idea. I mean, I essentially agree with you, right? That this delay is way too long to be explained by, you know, the lifetime. I mean, maybe you could have some proto-neutron star living for that period of time. That's probably too long. Another question that's actually pretty closely related, maybe to this delay timescale, if it has something to do with interaction with material around it, is also for Monsi. I'll take you off mute this time ahead of time. So Milton Ruiz at UIUC asked if the observed low luminosity short gamma ray burst is due to a circumbinary cocoon rather than an off-axis relativistic jet. Is the total electromagnetic luminosity emitted from binary neutron star merger comparable to a typical short GRB? Do you have a sense of that from this model you were talking about?
So if you look at the bolometric luminosity, it's there in the paper. That's actually only a couple times 10 to the 41 ergs per second. In an on-axis short-hot gamma ray burst, you see the afterglow component, which is much more luminous for a much shorter time. In this case, the bolometric luminosity evolves on several day to few week time scales, and it's overall it's lower than what you would expect if you had this ultra-relativistic jet that you were face on, looking down the barrel of the jet and seeing an afterglow component as well.
So it's somewhat underluminous from what you would expect from a regular short gamma ray burst. Okay, interesting. And he had a second part of this, but I think you more or less answered this, which is the luminosity observed when integrated over all EM wavelengths. I think that you answered that. Or is there, how much of this energy might be converted into kinetic energy in the outflow? Is that a significant energy loss? And I think that's the case for kilonovae, right? Is that
right? And in fact, I mean, the kinematics here are very interesting, because the kinematics here could suggest that some of the ejecta is moving so fast that the assumption that you use Newtonian velocities in all of these kilonova simulations may not be quite right. And so you might need to actually take into account relativistic effects of these velocities, and that can again explain this bright blue early emission that we see if material is in fact accelerated to few tenths the speed of light.
Cool. Thanks. So we also got a number of questions about the tidal deformability of these neutron stars related to Jocelyn's talk, and so I think Jocelyn can help answer some of these, and I'm sure Jim and other people will also have some thoughts. So Farouk Fatoyev at Indiana University just wanted to know if Jocelyn could elaborate more on the sudden change in the lambda 1, lambda 2, 90% confidence contour plot in the upper top corner. Does this have any implications on neutron star masses or radii? And also Chuck Horowitz, who's also at Indiana, also asked about how much is the lambda equals 0 deformability disfavored by data? Is it disfavored at all, or just that you have this upper limit?
Yeah.
Oh.
Really sure what the top corner.
Yeah, so I just have the question that he asked. So it just says that there's a large lambda 1 and a small lambda 2 section in the upper top corner. So is that?
So, I mean, so one of the things we see is with the wide range in mass ratios, the deformabilities can skew to have a very compact, more massive star and a very deformable low mass star that would be compatible with the masses, although not so much with our recovered tidal deformabilities. We do, so you can see in the distribution that the most favored values are a little pulled away from the lambda equals 0, lambda equals 0 sort of binary black hole equivalent corner, although that is more sensitive to waveform systematics that are still under exploration. So, you know, it's not a distinction from the binary black hole case that we can make at, say, the 50% level even.
Okay.
At this point. There's some hope with some of the ongoing reanalysis with improved waveform models, we might be able to say more, but it may just be that, you know, with more compact neutron stars, they're more challenging to distinguish precisely from black holes. And so, especially with the current sensitivity of the detector has increased noise fluctuations at the high frequency where the merger happens. So for this signal, that may remain masked by the noise.
Okay.
Jocelyn, one thing is a couple of people mentioned earlier, but it's probably worth saying explicitly is the error on the waveforms is a big source of errors for us right now. That measuring these nuclear effects, you know, the vacuum waveforms can be calculated very, very precisely, but obviously when you throw in the nuclear physics into binary neutron star mergers, things get much less accurate. And to the level of the effects we're trying to measure right now are of the order of errors in the numerical simulations. And so a lot of work is also going to be needed. We can improve with the models. We have better models than we want the ones we used in the paper, but they're still not perfect. So there needs to be a lot of work on improving those numerical models of the bi-neutron star mergers.
Okay. So for this question about the large lambda-1, small lambda-2 in sort of the upper corners of the plot, right, where I guess you have the largest mass ratios, maybe, are those what you're showing there is not really constrained by any equation of state model, right? It's just coming purely from what you get from the in-spiral data. Is that right?
Right. So that yeah. So we do see. Really, the constraint we make on the tidal deformabilities is not so much on the component tidal deformabilities, but on some combination of them. And so there's a sort of a degeneracy in the gravitational wave signal between, say, an equal mass system with some moderate tidal deformability on each star, and a more unequal mass system where one of the stars as the star gets more massive, it becomes much less deformable. Typically, the radius may decrease, but the mass also has an effect on this. And conversely, a low mass star has a much larger tidal deformability in terms of how it feeds into the gravitational wave signal. So we can't really tell with this signal whether we had sort of two moderate stars or one compact and one large star. Okay.
But even those large mass ratios would be consistent with, you know, predicted nuclear equations of state, or is that?
Oh, I mean, yeah. So at some point, you know, if you've put in assumptions about the equation of state generating the stars, those come in with maximum mass assumptions, and those right now that's not in our analysis. We allow the masses and the tidal deformabilities to vary entirely independently, freely over the range. But you know, to fully kind of make a consistent picture of what we were saying about a neutron star equation of state describing both stars, that to do that properly requires you know, the equation of state assumed has implications on the allowed masses, and that can become a little more complicated in the analysis.
If I could comment.
Go ahead.
I think that quote unquote realistic equations of state don't predict much of a radius variation for stars in the range between 1.2 and 1.6 or 1.5, where these two stars are likely to be. So in that sense, the tidal deformabilities will depend mostly on the masses rather than on the specific radii. The radii will be set generically by the equation of state and won't vary by more than a few tenths of a kilometer for stars in that mass range. So I think to infer that the information is such that that two vastly different lambdas implying two vastly different radii stars is simply not a realistic extrapolation.
Yeah, that's a good point. The lambda parameter depends on the combination of the mass, the radius, and the Love number. So that combination is not necessarily suggesting, for example, that, you know, the radius difference is proportional to the lambda or the tidal deformability difference.
Okay, excellent. Thank you. So another question that we had, going back a little bit to kilonova stuff, and maybe either Dan or Monsi want to answer this one. I think Monsi was the person who said this, is that someone had asked, why is it a surprise that the electromagnetic signal, at least the optical electromagnetic signal, was bright and blue? So what was the surprise there?
Well, I could say, I wouldn't say it was a total surprise that it was blue at early times. I mean, that was part of the theoretical picture that we had prior to it, that you would likely, based on simulations, have these different components of ejecta, some parts that were less neutron rich and made low opacity blue optical emission, and others that made longer lasting red emission from heavier elements. So I think that two-component picture was there, and there were models done that showed, you know, some blue emission that was, you know, maybe a factor of a few dimmer than what was seen. So, but it, you know, whether you had that blue emission or not depended upon certain conditions in the merger, whether you really could produce those low element species, which depended upon details that we didn't know. So it could have been that there was no blue emission, but there could have been some significant amount. And the amount we saw was actually at the very high end of what we had expected. And so we were lucky in that regard. And the masses inferred of that blue component of you know, a few hundredths of a solar mass are you know, they're on the high end of factor of a couple compared to simulations, which typically get maybe up to 1% or so. So I think within the uncertainties that we have, it's consistent, but you know, we were lucky to be on the high end of that blue component rather than the you know, the absence of it, because it would have been a lot harder to find had it been dimmer in the optical.
Yeah, and I'd just like to add that the first ultraviolet observation was 14 hours after merger, and it was 17th mag. And you know, while there were models that predicted some blue emission, most of the models that predicted bright blue emission was on the few-hour time scales, not half a day, more than half a day later. And the luminosity was just so high that you know, I think you can always crank up some parameters in mass and velocity and lower the opacity to try to make this work. But it does require pushing to you know, uncomfortably a little bit higher than what existed in predictions. And so I think we should be open to different ideas on what this early bright blue emission is. And I think one of the biggest open questions in future events is, what does that blue emission do in the first 12 hours? Does it just fall like a rock, or is there a finite rise and then a decline? And that can distinguish between the various ideas out there on what could give such bright blue emission for a sustained period of time.
Thanks. Yeah, so maybe a related question. A question I sort of had that relates to a question that someone asked is, so Sam Austin here at Michigan State University is just asking how many kilonovae have been observed. For instance, one obvious case is maybe GRB 130603b, the afterglow there. So would you have expected to, if the blue component there looked the same as it looked in GW 170817, would you have expected to have observed that in this other instance of a kilonova that we have? Brian looks like you might have some thoughts. I'm sure Nancy does too, so everyone can fight. You're muted, Brian, just a second.
Well, okay. I mean, I think Nancy can address better whether or not we would have seen these in previous surveys. My understanding is it's hard because even though they're bright, they're rare and they're fast evolving, and we until recently haven't had many surveys that could see these. But I'll let her answer that. I do want to push back a little bit. I will say that, you know, I think even back in our 2010 models, you know, fit to this event, we can actually get something very similar to the blue emission that was observed. Now, of course, we were assuming things like very high thermalization efficiencies, but I would say that you know, the idea that these bluer models weren't in place is I would say not entirely correct. But I would also say, you know, pushing what she also said about the early you know, mission on a few hours, I agree. That scale is, you know, if we can get on the next one, this one happened over the Indian Ocean, so everyone had to wait for 11 hours for, you know, to rotate so people could observe it in Chile. If we have one over North America that we can view with Palomar, Nancy can view, we may be able to get on very early. And that would be very exciting because there we're probing the very outer layers of this material. Whether, you know, one thing that can happen is if the matter expands very fast, you can actually get a freeze out of the R process, which leaves a bunch of free neutrons in the outer layers. And those neutrons have a fairly long half-life compared to the typical R process nuclei. So they dump in a lot of energy on a timescale of a few hours. And that's actually would be really interesting to probe because it actually would be sensitive, I think, to the conditions in the ejecta and some of the nuclear properties near the waiting points, which control whether the R process might freeze out. But it could also be that this cocoon emission contributes there. So if we see it, you know, this hot shocked material as the jet breaks out of the material, out of the ejecta. So I think yeah, that those first few hours is a lot of key information, and it would be great if we could get on earlier. That's all.
And if I may add about the short-haired gamma ray bursts that previously have claimed to have kilonova components, there are 5 such claims out there. And if you assume that GW170817 is now the new truth function and what an excess emission was, these 5 previous claims were sort of fraught with one data point being in excess of what you expect from an afterglow and potentially coming from a kilonova. And if you just overplot what that one data point based claim was, then GRB 160821b and GRB 050709 fall exactly on top of the light curves of GW 170817. GRB 130603b, Luke, the one that you mentioned, the most famous as far as media goes on this, is actually a little bit higher, about half magnitude higher than EM 170817. So it still requires pushing the ejector masses even higher to explain in this context. And the 2 others don't land, are not consistent with this.
Thanks. That's a great answer.
Luke, just to add something on the timing, given that people mentioned this, there's in principle no reason why LIGO Virgo couldn't get alerts out in a few minutes. This was a both lucky and unlucky case that we had this type of known class of glitch landing on top of it that took some manual processing. We actually already had software that automatically removes those glitches from the analysis, but we turned it off in the low latency search for fear of vetoing something loud, a short loud signal. So we already have tools in place to take care of that. So we should be able to get these out in order minutes in future in 03.
Thanks. So while we're still talking about the kilonova stuff, we'll switch over a little bit to some questions people had about nuclear physics input for the models and things of that nature. But sort of one last question. I think it's important to answer this, I think, is that, so someone had asked what elements were actually directly identified in the spectra. They thought that some particular heavy elements were created and were seen, and is there any evidence that other heavy elements were created there? So I think, mentioning that maybe we don't, see direct signatures of any particular element might be useful to say, and what signatures we have. So Dan's probably maybe the person to talk about this.
Yeah, it's hard to say because as I mentioned, you see some features in the infrared spectrum. The optical is basically featureless. And it's largely because there's a lot of lines involved and they all get blended out and make some features that are kind of composite features. Now, as Monsieur and I showed, some of the models that we had done kind of fit the locations of those peaks fairly well. And the dominant element that was producing those peaks was neodymium, which is one of the well, first of all, it has an atomic structure since it's a lanthanide that's quite complex, so it naturally has a very important effect on the opacities and emission. And of the lanthanides, it's one that's made in large abundance, we think, in our process. So that may be one of the key players in shaping that spectral behavior. But it's hard to say at these early days. I mean, we don't have great atomic data and line lists for all the many elements across the periodic table that can contribute. And they contribute in a non-trivial way as they blend together. So we showed as a proof of principle, as we varied abundances in the ejective, we changed the amount of neodymium by some factor or increased the amount of some other element like cerium. It changed the locations of peaks in the spectra. And so I think over time, as we understand the nuclear physics and heating better, and we understand the atomic physics of the lines better, we can dig into that and say in some more detailed way what elements are contributing. But at this point, there's some hint of neodymium playing a role with some uncertainty, and I think other attempts at line identification are not very reliable.
Thanks, Dan. So now there are actually a bunch of questions about sort of what sort of nuclear physics input might be sort of the most important things to put in, especially the simulations and how we interpret these events. So maybe Andreas is the person to answer this one. He already touched on it a little bit, but maybe in a little bit more detail. It's just what nuclear physics input is needed for neutron star merger simulations, and maybe what's the most important input? What should the nuclear physics community be going after to really constrain what's happening in the central engine of these things better?
I think the dynamics of the merger and the gravitational wave signal and the dynamics of the mass ejection are, of course, all determined by the equation of state. So the equation of state is the key to all these observables. And so I think the most important property of the equation of state determining the dynamics is probably the pressure as a function of the density. So essentially, you could also translate it into the radius of a neutron star. And so this relates essentially to the slope of the symmetry energy, if you want to hear some nuclear physics parameter that is the most relevant maybe for the equation of state or for the properties of the equation of state. So I think this is what is probably the most important, that is determining the overall dynamics of a merger.
And so, sort of which nuclear physics input is likely to be the most important? Is it, like you mentioned, measuring the symmetry energy, the density dependence of the symmetry energy, or is it is it low density nuclear equation of state that matters, or what's happening at very high density near the neutron star core?
I think measuring the slope of the symmetry energy would be extremely helpful, and everything else that you could measure above saturation density would be, of course, also very helpful if this is possible. But fixing the pressure at a given density would be already very, very, very helpful. To which extent the low density part really affects, for instance, the gravitational wave signal is probably questionable, because the bulk mass affects the gravitational wave signal, and it also affects the overall dynamics and therefore the mass ejection. So I think what is going on at higher densities is the most relevant here.
For the gravitational wave signal.
For the gravitational wave signals, but also for the mass ejection, because the mass ejection is somehow triggered by the dynamics of the total system.
Yeah, but
could be the impact of the low density part as well.
Its composition, you're going to have to go through low density material to eventually to get out. So getting stronger constraints on the equation of state is one aspect. We'd also, I think we'd also like to think about, what sort of measurements are the next things that we can do to constrain that. I know that we didn't talk too much about like heavy ion collisions and those sorts of experimental measurements, but I don't know if Ani or Artemis want to comment just a little bit on what the sort of the prospects are for getting some constraints on the nuclear equation of state from the terrestrial laboratories.
Yes, Luke, if I could just say something, I appreciate Andreas's point about the equation of state, that's kind of an overall effect. But if you look for in our process with the individual nuclear properties like masses, neutron capture rates, beta decay rates, and beta delayed neutron emission probabilities, out of those, we have shown in lots of sensitivity studies that the masses play the biggest role. They have sort of the biggest impact on what is produced. And Dan Kaysen also showed some plots with different mass models, depending on which of our process peaks get populated, depending on what limits are used. So in a way, nuclear masses are the most important thing right away. They have a bigger effect.
If I could comment?
Go ahead, Jim.
So I think that we're saying the same thing. I think that nuclear masses extrapolated to very neutron-rich nuclei depends very sensitively on the density dependence of the symmetry energy. And that's precisely what controls the radii and the tidal deformabilities of neutron stars, which are the most immediate things that are measured from these gravity wave events. And I should also mention that there are upcoming astrophysical studies that can also bear on this, but we're focused more here on nuclear studies. And so the next generation of the PREX experiment, for example, could be very, very influential here as well in getting a systematic free, if we could, determination of the neutron skin thickness. which is very closely correlated to both these properties, neutron star radii and the symmetry energy density dependence.
Thanks, Jim.
Yeah, and maybe if I can add as well that in terms of measurements for the equation of state, I'm not an expert, but I know already people are doing experiments where they're trying to use symmetric matter, so equal numbers of protons and neutrons, and then use nuclei that are very asymmetric, very neutron rich, and then do comparisons, do heavy ion collisions and do comparisons. And so then with the next generation facilities and with every, because we can go even more neutron rich, we can probe even larger asymmetries.
And that'll hopefully get us some constraint on symmetry energy at and around saturation density, right? Another question that relates to sort of some nuclear physics uncertainties, and Dan touched on this a little bit in his talk, but this also comes from Chuck. Chuck is asking many questions today, as usual. So it's how do nuclear physics uncertainties impact heating in these kilonova and the ejecta masses? And then maybe a follow on to that, what could we go out and measure that would help better constrain what are heating efficiencies in the kilonova ejecta and things like that. So I'm sure that many people on the panel who might have something to say about this. So whoever wants to go first can jump in.
I could say that's one of the key uncertainties, because the different nuclear mass models, for the same initial conditions, will produce different abundances of elements and different radioactive heating rates. And the differences can be factors of several, 4 or 5, and at later times in particular, orders of magnitude or such. So, and so that directly goes into our estimates of how much mass is ejected. We need to know quite well what the nuclear heating rates are. And one handle we may have on it is observationally to probe it, is to look at the late time observations of kilonova, because it's there where you tend to see the biggest differences between the nuclear mass models and the heating rate models that would predict heavier translate elements that produce more alpha decay will thermalize more effectively at late times and produce a brighter kilonova. So there's some interplay there between learning more about the nuclear physics and comparing it to sort of long baseline kilonova observations.
Thanks, Dan. Ani, you had a comment? You're off mute now, sorry.
I was just going to, I was just going to ask Dan, actually, specifically what the heating is resulting from directly, which nuclear property contributes the most? Besides the entire mass of the ejecta, what nuclear property determines that?
You mean what's the nuclear decay pathways that are controlling this?
Is it just a decay?
Yeah, I mean, primarily it's beta decay of these neutron-rich nuclei back to stability. So those are producing gamma rays and fast electrons. The gamma rays will, after a few days or so, they typically can escape the ejecta and say they're no longer efficiently heating. But the electrons, the betas, will be trapped longer and will be able to heat more efficiently at longer time scales. And then for the heavier nuclei, they can also undergo alpha decay or maybe even spontaneous fission at late times. And that those products, the alpha decay products, will probably thermalize more efficiently. And so that's one of the distinctions between different mass models, is how much alpha decay you get from your particular nuclear model at late time once the betas start escaping it more effectively.
Yeah, some of the work that we did showed that it's not so much dependent on which nuclear masses you use, but the astrophysics trajectories for a merger versus a core collapse supernova are different enough that they emphasize different nuclear, different beta decay rates. So I think that if we're able to measure those beta decay rates to high precision, we'll be able to say something about that. the heating aspect too.
Yeah, that would be fantastic to better understand that heating. And yeah, as you go to later times, things are decaying back down to stability, so they're not as far away from stability as maybe the path originally was. But the path itself will set what isotopes are there at the beginning to decay down.
Yeah.
Then if I can ask a question too.
Yep, go for it.
So does it matter how the energy gets distributed between the gamma rays and the electrons and the neutrinos in this process?
Yeah, very much so, because yeah, the neutrinos are just going to escape immediately. The gamma rays may be trapped for the first day or a couple days, but then they escape, and then the electrons are more effectively thermalized. So, you know, how bright the kilonova is a function of how much energy is coming out in those different channels, how much energy gets thermalized. And so if we change those, if we figure out that those are different than our kind of default assumptions now, that changes our estimate of what the kilonova, how bright it should be and what the mass involved is.
I just wanted to add to that, which is just that, you know, when we have very neutron-rich matter, which, you know, shoots up to the heaviest elements, and we maybe get fission cycling, all these things, we tend, even without fission cycling, we tend to get a radioactive decay, you know, in terms of, which is, you know, it's some kind of power law, or it's usually a statistical combination of many nuclei. But if we have less neutron-rich matter, like in this event where we see that there's some matter that didn't produce such a wide distribution of nuclei, what you find, and Luke can comment on this as well, is that the heating is sometimes dominated by actually a few nuclei, or you see more bumps and wiggles. And so in that case, I think the higher, if you go to higher YE, less neutron-rich matter, I'm guessing the heating rates that we infer become more sensitive to some of the individual decay times of these nuclei. And I don't know if this would be possible, but if we at some point saw something that looked like an exponential decay in the light curve of some nucleus, you know, being able to match that half-life to something we measured in the laboratory would be cool. It's a bit ways off, I think, but you know, it's something to think about. So maybe Luke wants to say something more about that.
Yeah, I think you said most of it. I'm just the moderator, not supposed to comment too much. Okay, so I think we're probably pretty close to wrapping it up. Well, one last question that was pretty interesting that we got for the sort of nuclear experimentalists, and this sort of feeds back on what we were just talking about now, is what are the implications of this event for you? I mean, what sort of different measurements are you thinking of going after that you were maybe previously not thinking of going after? Do you think this opens up sort of new directions that you want to go into? Artemis, I guess you can start, and you can say something about it.
Yeah, sure. So I mentioned earlier that before there would be sensitivity studies on all different varieties of astrophysical scenarios. And so then each of them would predict different nuclei being important. And then from our point of view, we would basically have to measure everything. So it's important that now we know which nuclei we should be targeting. The other thing is that since this colder, very neutron-rich scenario, we know that it goes much further from the stable isotopes. It's maybe even all the way close to the drip line, to the neutron drip line. So we know that we really have to reach to those most neutron-rich isotopes, and that's what we're getting with FRIP, which is great. And then the last one that I kind of briefly mentioned in the talk is that if we are not in a n gamma n equilibrium, that means now that the neutron captures matter, which was not so much the case if you are in equilibrium.
Thanks. So I think we'll sort of maybe wrap up here because we're getting quite close to 3. And so sort of as just a final thing, I think everyone on the panel, I just want to hear from everyone on the panel sort of what's the most exciting opportunity going forward from GW 170817. So I just give a sort of a brief answer, what you think is maybe the most, the most interesting new research direction, maybe the most interesting puzzle that's been left behind, or what's sort of going forward. So maybe we can start with Duncan on this.
I think the most exciting thing here is the fact that we are going to be detecting a lot of binary neutron stars moving forwards, and we're just going to get more and more of them as LIGO reaches design sensitivity. I mean, this signal, if it had been more favorably oriented, would actually been detectable by initial LIGO, which is somewhat remarkable. And there seems to be this gap between the GRBs that have redshifts and GRB 170817. There are fainter GRBs that have always been assigned to being at large redshifts, but perhaps they're actually much closer than previously been thought. And so we might actually be seeing quite a few of these joint observations much more quickly, which will provide a lot more data in the years coming forward. So I think that's, for me, that's, as an observer, that's one of the most exciting things going forwards.
Excellent, thanks. Monsi, what are your excitements?
I'm excited about many things, given that the future seems to be quite literally bright and loud. So one of the things I'm very curious about is what a neutron star black hole merger would look like. So Duncan, you guys have some work to do to find that one soon. And of course, I mean, this question of, there's so many models, earlier data would be even better in the first few hours. Is the Cocoon model really correct? And, I mean, I think a larger sample would tell us this answer. And this is just the beginning. It's really exciting.
Excellent, thanks. Brian? You're on mute.
Okay, okay.
There you are. You're good.
Hi, yeah, okay. Yeah, I mean, I think for me, one of the exciting things that I sort of realized, is there's this interesting coincidence in this event between the delay until the gamma ray burst, and which is a few seconds, and actually the time it takes for the R process to complete. And so now that we're starting to talk about jets breaking out of giant cocoons, one of the things I'm seriously thinking about is the R process. We used to think of it just sort of this ejection of material. In a few milliseconds, it expands into space. The R process happens in a way that's sort of independent from what's going on at the central engine. I'm now beginning to think, well, maybe it's not so simple. Maybe there's interplay between these different components. Maybe the matter is shock heated again as it's going out, and this can produce more complex thermodynamic history for the R process material that was produced. So to me, that's the fascinating thing, is this sort of, we're getting this evidence, as Monsi said, that from this cocoon possibility that there may be interplay, more complicated thermodynamics going on than we originally thought. So,
excellent, thank you, Brian. So Jocelyn, what are your thoughts on what's maybe most exciting going forward?
Yeah, so I mean, of course, the prospect that this is going to be a common occurrence in a few years is really delightful. But I think, I think one thing that I think is fascinating right now is just trying to best figure out how we can feed in all the information we have about the properties of neutron stars we see, the numerical simulations, the best guesses for how it's possible that the neutron star equation of state might behave, and see if we can do a better job even of analyzing this first neutron star merger going forward. I think the story's not over yet for understanding this one signal. So I'm really looking forward to creative ideas for how to best interpret what the data is telling us.
Cool, great. Jim, what are your final thoughts here?
Yeah, I'm of course was so excited by this event that I could hardly imagine what might happen if we see a neutron star black hole merger. And I think my feeling is that the predictive power that computational astrophysics has been able to achieve has just been fantastic, and really justifies moving forward in this direction. And so I anticipate that these next observations are going to help us constrain things even further. It's remarkable how a single event has really changed things. So good.
Thanks. Dan, what's your sort of final thoughts here?
Yeah, lots to be excited about. I think in particular the fact that we have this, after years of trying to tease out where the R process was by looking at its trace abundances in stars and meteorites, we have now this pure sample of our process right at its production site, and we can try to analyze that. And it was one thing that was surprising about this event, the kilonova, was that it was not all that surprising in its behavior. It, to first order, kind of matched the predictions of what we thought it might look like. But who knows, as the diversity events and we get more kind of mergers, will they behave so well, or will they throw some surprises at us? In any case, there's a program going forward to try to see what range of behaviors we get and try to probe the heavy element production in more detail.
Excellent, thanks, Dan. Andy, what are your final thoughts here?
So I think I share my excitement with Dan that I would really like to see many more neutron star mergers and to understand the diversity of these events and really to compare different events and to see how much they differ and what this tells us actually. I think this would be something very exciting, and then to join different constraints on mass ejection and the equation of state. And another prospect that I find very exciting is that, I mean, this was a relatively close event, and as we approach design sensitivity, we might have the chance to detect also post-merger gravitational wave emission, which could tell us something about the fate of this merger run and if it collapsed directly or whether it produced a hypermassive neutron star or maybe even a supermassive neutron star. And this could tell us a lot about the dynamics going on in this thing, and this I find very exciting for the future, I think.
Excellent, definitely super exciting. So Artemis, what are your what do you think the most exciting opportunities going forward from this are?
Well, I'm really excited to use now nuclear physics, current data that we have already, but also future data with FRIB to try and interpret the observation even better. And I'm learning all the time, even now with the discussion about heat, that there's even more nuclear physics that we need to be looking at. So I'm really excited to go and attack these problems.
Excellent, thanks. And then Ani, you're the last word here. Oh.
Yes, I think this observation has made it even more important that we go out and measure the most neutron-rich nuclei, because we've already at least identified a set of nuclei that would be more important for neutron star mergers than for other types of our process scenarios. So for me, it would be really exciting if we could measure those and then be able to duplicate the light curve that so many people are observing. And if it's true that we're going to see about 40 a year, I think there's a lot of excitement. But the merger nuclei, that neutron-rich nuclei, are a lot more neutron-rich than some of the other things we've set our eyes on. So the challenge is open, and it's really exciting for us to go there.
Awesome. Thank you. And thank you to everybody, both the speakers and all of our panelists. The director of JINA, who also organized most of this and made this event happen. And I also want to thank everybody who sent in questions via Twitter or email. Sorry that we didn't get to all the questions that came up. There were a lot of good questions, and if people want to answer other people's questions on Twitter, that would be great. So hopefully everyone enjoyed this event, and thanks for tuning in and watching.